In this video, we'll be looking at right triangle trigonometry, and we'll be focusing on the 6 trig functions. Those are sine, cosine, tangent, cosecant, secant, and cotangent. To introduce these, let's look at this right triangle. Recall a right triangle has a 90-degree angle, and we'll be focusing on this angle theta to create these 6 trigonometric functions. Notice the side opposite the angle theta we are calling B. The side adjacent to angle theta, adjacent means the side touching the angle, we'll call side A. And then the longest side we call the hypotenuse. We'll label that as C. So focusing on this triangle, sine we can shorten or abbreviate as sine of theta, sin theta. Its relationship is opposite over hypotenuse. So the side opposite divided by the hypotenuse, the longest side. Cosine, which we shorten to cos theta, is adjacent, the side adjacent theta divided by the hypotenuse. And tangent, we abbreviate TAN or tan, that is opposite over adjacent. Cosecant is going to be the reciprocal of sine. The abbreviation for cosecant is CSC. Since it's the reciprocal of sine, cosecant theta will be hypotenuse divided by the opposite side. Secant, which we abbreviate SEC, is the reciprocal of cosine, or hypotenuse divided by adjacent. And cotangent, which we abbreviate COT theta, is the reciprocal of tangent, or adjacent divided by the opposite side. Next, we'll look at these again, just using shorthand. I'm going to draw the same triangle. We have the adjacent side A, the opposite side B, and the hypotenuse C. Sine theta, again, is opposite over hypotenuse. So using this triangle, opposite is B divided by the hypotenuse C. Cosine is adjacent over hypotenuse, or A divided by C. Tangent is opposite over adjacent, or B divided by A. And we already know that cosecant is the reciprocal of sine. So we just need to flip that fraction, and we'll get C divided by B, or hypotenuse over opposite. Secant theta is the reciprocal of cosine. We get C divided by A, or hypotenuse over adjacent. And cotangent is the reciprocal of tangent, or B, A divided by B. Now, I realize students don't always like to memorize different things because there's so many different formulas and equations in math that you are expected to memorize. This is one of them. But really, you only need to know the first three. If you know the first three and their relationship, you can simply come up with the others by doing the reciprocal like we did earlier. There is a mnemonic, SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. SOHCAHTOA is a mnemonic that is helpful to memorize the first three, and we can come up with the other three using the fact that they are the reciprocal of the original SOHCAHTOA. Let's look at this example. Consider a right triangle with an angle theta such that the adjacent side is 12 and the opposite side is 5. Let's sketch that. We have a right triangle. We're told that the opposite side is 5 and the adjacent side is 12. We want to find the missing side. In this case, we're trying to find the hypotenuse. Recall the Pythagorean theorem. A squared plus b squared is equal to c squared, where c is the hypotenuse. We have 12 squared plus 5 squared equals c squared. 12 times 12 is 144. 5 squared is 25. 144 plus 25 is 169. That's equal to c squared. And we want to find c, so we'll take the square root of both sides. And we get that c is equal to 13. Technically, we're supposed to do plus or minus here because we took the square root of both sides, but we're looking for the length of the side of a triangle, which we know to be positive. So we'll stick to just the positive 13. For part B, we want to find the exact value of each of the 6 trig functions. Let's use SOHCAHTOA to help us there. SOHCAHTOA. But first, let's find sine theta. Sine theta, we have opposite over hypotenuse. So when looking at theta, the side opposite is 5. The hypotenuse is the longest side, 13. So we get 5/13. Now cosine. Cosine theta is adjacent over hypotenuse. So the side adjacent is 12. The longest side, 13. We have 12/13. And then tangent. Tangent theta is opposite over adjacent. Opposite is 5, adjacent is 12. To find the other 3, we can remember the reciprocals. The reciprocal of sine is cosecant. We have cosecant theta. It is simply the reciprocal of sine. So we get 13/5. And then the reciprocal of cosine theta is secant theta. Flip that fraction, we get 13 divided by 12. And then the reciprocal of tangent is cotangent theta. Its reciprocal is 12/5. In this topic, we'll introduce 2 new identities, reciprocal and quotient identities. Earlier, we noted that cosecant theta is the reciprocal of sine theta. So we can write cosecant theta as 1 divided by sine theta. Similar to that, secant theta we can write as 1 divided by cosine theta. And cotangent theta we can write as 1 divided by tangent theta. These are known as the reciprocal identities. Then we also have quotient identities. One common one that we'll see quite often is tangent theta. Tangent we can write as sine theta divided by cosine theta. And then, as we saw earlier, the reciprocal of tangent is cotangent. So cotangent theta is cosine theta divided by sine theta. Let's look at using these. If we're told that sine theta is the square root of 10 divided by 10 and cosine theta is 3 square root 10 divided by 10, let's find the 4 remaining trig functions. Up first, tangent. Remember that tangent theta is sine theta divided by cosine theta. Sine theta, we are told, is the square root of 10 divided by 10. And cosine theta, we're told, is 3 square root 10 divided by 10. We have a fraction divided by a fraction, so we can keep the first fraction the same and multiply by the reciprocal of the denominator. Simplifying this, we get 1/3. For cosecant theta, recall from earlier, the reciprocal identity. Cosecant theta is the same thing as 1 divided by sine theta. And we were told sine theta. Sine theta is the square root of 10 divided by 10. 1 divided by a fraction we can rewrite as just the reciprocal of that denominator. We get 10 divided by the square root of 10. Now, while that might look simplified, we typically don't want square roots in the denominator, so we need to rationalize the denominator. And we can do that by multiplying by a funny looking 1. But very specifically, we're going to take that denominator and multiply the numerator and denominator by that value. And this will give us 10 square root 10 divided by root 10 times root 10 is the square root of 100, which we know to be 10. And then this simplifies to just the square root of 10. Up next, we have secant theta. Remember that secant theta, we can look at the reciprocal identity. We know that secant theta is 1 divided by cosine theta. And in this case, we were told what cosine is. Cosine is 3 square root 10 divided by 10. We can again flip that fraction. Since we have 1 divided by a fraction, we'll just flip the denominator. We have 10 divided by 3 root 10. And again, we need to rationalize that denominator. We'll multiply by the square root of 10 divided by the square root of 10. This will give us 10 square root 10 divided by 3 times square root of 100 is really 3 times 10 or 30. And then that will reduce to the square root of 10 divided by 3. Finally, cotangent theta. We know it is the same thing as, we could do cosine theta divided by sine theta, or we could just use the fact that cotangent theta is 1 divided by tangent theta. We have options, and in this case, if we use this version of cotangent, we'll have to deal with 2 different substitutions, whereas if we just think of cotangent theta as the reciprocal of tangent, and we already have tangent, we can simplify this a little bit easier. So that will be 1 divided by tangent we found to be 1/3. And then we can simplify this to get 3. For topic 3, we'll be looking at 3 important identities known as the Pythagorean identities. Now I know what you're thinking, great, there's just more identities that I have to memorize. And it's true, while knowing them is going to be beneficial to you, you really only need to know the first one. And if you know this one, sine squared theta plus cosine squared theta equals 1, you can relatively quickly create the others. Let's see that here. Let's start with the original sine squared theta plus cosine squared theta equals 1. And let's divide both sides of the equation by sine squared theta. So we'll divide each term by sine squared theta. And notice what we get. Sine squared divided by sine squared, that is 1. And then cosine squared divided by sine squared, that is cotangent squared theta. And 1 divided by sine squared theta is cosecant squared theta. Notice what we just created. We just created the second Pythagorean identity. So if you have the first one memorized and know that we can divide by sine squared on every term, we can relatively quickly create that second identity. And notice we can also manipulate that result and solve for cotangent squared theta. So if we subtract 1 on both sides of that equal sign, we'll get cotangent squared theta is cosecant squared theta minus 1. This is the same identity, just manipulated a little bit so that cotangent squared theta has been isolated. Sometimes that can be helpful. Let's again start with sine squared theta plus cosine squared theta equals 1. But this time, let's divide every term by cosine squared theta. This first piece, sine squared theta divided by cosine squared theta, is tangent squared theta plus cosine squared divided by cosine squared is just 1. And then 1 divided by cosine squared theta we know to be secant squared theta. And look at what results. It's the third Pythagorean identity. That's convenient. We don't have to memorize all 3 if we know the first one and know how to manipulate them to get the other 2. We can also, if we wanted to, solve this identity for tangent squared. So we'll subtract 1 on both sides to get secant squared theta minus 1. And sometimes that's helpful when we're looking for just tangent squared theta. In example 4, we want to use the Pythagorean theorem and the following triangle to prove each of the following. So we'll go through and prove these identities. Note that we have a right triangle denoted by this angle here. And the Pythagorean theorem states that a squared plus b squared equals c squared. That is where a and b are the legs of the right triangle and c is the length of the hypotenuse. We could also manipulate this Pythagorean theorem to isolate different letters. So right now we have c squared by itself, but let's say we wanted to get a squared by itself. If we wanted to get a squared by itself, we would need to subtract b squared on both sides. And that will give us c squared minus b squared equals a squared. Similar to that, let's say we wanted to isolate b squared. Going back to the original Pythagorean theorem, we would need to subtract a squared on both sides, and we would get c squared minus a squared equals b squared. You'll see why we did that in just a moment. Recall from earlier, we used the mnemonic so katoa to help us recall the 6 main trig functions. Sine squared theta. Sine, recall, is opposite over hypotenuse. So if we're focusing on this theta, we have b over c. But it's being squared. Plus cosine squared theta. Cosine, remember, is adjacent over hypotenuse. So we're looking at a over c, quantity squared. And we want to prove that that is equal to 1. Well, notice we have a fraction squared. We can simplify that by squaring both the numerator and denominator. B squared divided by c squared. And we'll do the same thing in the second fraction. We get a squared divided by c squared. And notice we're adding fractions and they have the same denominator. So we can combine that into a single fraction, b squared plus a squared. And recall what we set up here. A squared plus b squared is c squared. So let's replace that numerator, b squared plus a squared, with c squared. C squared divided by c squared is 1. So we've proven that sine squared theta plus cosine squared theta is indeed 1. For the second identity, let's start by isolating the 1. So I'm going to subtract cotangent squared theta on both sides. 1 is equal to cosecant squared theta minus cotangent squared theta. Now let's show that the difference of these two functions is indeed 1. Cosecant, remember, is the reciprocal of sine. Sine is opposite over hypotenuse, so the reciprocal would then be hypotenuse over opposite. So that's going to be c divided by b. And remember that that is being squared. Minus. Cotangent is the reciprocal of tangent. So if tangent's opposite over adjacent, the reciprocal would be adjacent over opposite, or a over b. And that is also being squared. We can rewrite those. The fraction squared we can write as c squared divided by b squared minus a squared divided by b squared. We have common denominators, so we'll write that as a single fraction, c squared minus a squared divided by b squared. Earlier we said that c squared minus a squared is b squared, so we can replace that numerator with b squared. We have b squared divided by b squared, which is 1. Finally, the last identity, let's again isolate the 1. 1 is equal to secant squared theta minus tan squared theta. Secant is the reciprocal of cosine. So if we write the reciprocal of cosine, that will be hypotenuse over adjacent, or c divided by a. And that is being squared. Minus tangent. Tangent is opposite over adjacent. or b divided by a. And that is, again, squared. We'll rewrite those as c squared divided by a squared minus b squared divided by a squared. Combine those fractions, c squared minus b squared divided by a squared. And recognize up here we have c squared minus b squared is a squared. So let's replace that numerator with a squared. Keep the denominator to the same. And note that is indeed 1. For topic 4, we want to continue looking at the fundamental identities we've seen up to this point. As a reminder, cosecant theta is 1 divided by sine theta. Or we could write sine theta as 1 divided by cosecant theta. They're reciprocals of each other. So when we look at this first fraction, 1 divided by cosecant squared of 35, we can think of that as the reciprocal, which is sine squared of 35 degrees. And then we'll just copy the second part, cosine squared of 35 degrees. And remember, we also have the Pythagorean identity, sine squared theta plus cosine squared theta is 1. Since both thetas in this case are 35 degrees, we can say that this evaluates to exactly 1. In the next part, let's remind ourselves that tangent theta is the same thing as sine theta divided by cosine theta. Or cotangent theta is cosine theta divided by sine theta. So looking at our first fraction, we have cosine of pi thirds divided by sine of pi thirds. That we can write as cotangent of pi thirds. Minus, we'll just bring down the other cotangent of pi thirds. Cotangent of pi thirds minus cotangent of pi thirds is 0. So we can evaluate these without needing a calculator. In example 5, we're given that sine theta is 2/5 and theta is an acute angle. We want to find the exact value of the remaining 5 trigonometric functions. Let's sketch the triangle first. We have a right triangle. Theta, we are told, is an acute angle. Remember, that means an angle that's less than 90 degrees. And we're told that sine theta is 2 divided by 5. Remember, sine is opposite over hypotenuse. So the side opposite theta is 2, the hypotenuse is 5. We'll need to know this remaining leg. First, let's use the Pythagorean theorem to find that. A squared plus b squared equals c squared. So a squared plus b in this case is 2. We'll square that. And c is 5. A squared plus 4 equals 25. A squared equals 21. And then we'll take the square root of both sides to get a is equal to the square root of 21. Technically, we get plus or minus since we took the square root of both sides, but we'll use just the positive version since we're looking at length. Sine of theta, we are told in the directions, is 2/5. Let's find cosine theta next. Remember, cosine is adjacent over hypotenuse, so the adjacent side is square root of 21. divided by the hypotenuse, which is 5. Then tangent theta. Tangent is opposite over adjacent, so that is 2, divided by the square root of 21. And typically we want to rationalize the denominator. So let's multiply by the square root of 21 divided by the square root of 21. And this will give us 2 square roots of 21 divided by 21 for tangent. Cosecant theta is the reciprocal of sine. So we can simply write that as 5 halves. Secant theta is the reciprocal of cosine. So let's just flip that fraction. 5 divided by the square root of 21. We again, in this case, want to rationalize the denominator. So we'll multiply by square root of 21 over square root 21. This will give us 5 square root 21 divided by 21 for secant theta. And finally, cotangent theta. Remember, that's just the reciprocal of tangent. And I'm going to use the original that we had so we don't have to deal with the square root and rationalizing. So we'll just get the square root of 21 over 2. For part B, we want to find the exact value of cosine and cotangent. Let's assume we don't already know them. Let's assume we haven't already done part A. So we'll approach this slightly differently. We want to use the identities. So let's use the Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. We're told in the directions that sine theta is 2/5. 2/5 squared plus cosine squared theta equals 1. That will be then 4/25 if we square the 2 and the 5 plus cosine squared theta equals 1. Next we'll subtract 4/25 on both sides. 1 minus 4/25. If we want to show every step, let's write that 1 with a common denominator of 25 so that we can combine these two fractions. Cosine squared theta is 25 minus 4 is 21 divided by 25. We then want to take the square root of both sides to get cosine theta equals the square root of 21, and then the square root of 25 is 5. So we now have cosine theta. To find cotangent, let's use one of the other Pythagorean identities. 1 plus cotangent squared theta equals cosecant squared theta. 1 plus cotangent squared theta equals cosecant we can get using the reciprocal of sine. Remember, cosecant is the reciprocal of sine. So let's just flip that 2/5 to get 5 halves squared. We now have 1 plus cotangent squared theta equals 25/4. From here, we'll subtract 1 on both sides. 25/4 minus 1. We again need a common denominator so that we can combine those two. We can rewrite 1 as 4 divided by 4. Cotangent squared theta is now 21 divided by 4. We'll then take the square root of both sides. Cotangent theta is the square root of 21 divided by the square root of 4, which is 2. And recognize that the values we found here, cosine theta, is the same as what we have here for cosine theta. And cotangent theta, this value, is the same thing that we had over here for cotangent theta. We just found them using a slightly different technique. For topic 5, we'll be looking at complementary angles and cofunctions. Up first, a definition. Any two angles whose sum is 90 degrees are called complementary angles. Another good thing to recall is the sum of any three angles in a triangle. The three angles of a triangle add to 180 degrees. Notice that in this visual we do have a 90-degree angle, so we're looking at a right triangle. That'll be helpful for what we're doing here. In this triangle, notice that A and B are complementary angles, because if we look at the total measures 180 degrees and subtract this 90-degree angle, what's left over is 90 degrees. So that means A and B together make up 90 degrees. Which makes them complementary angles. Here we have that same triangle. Let's use some information that we now know about complementary angles to find sine, cosine of these different angles. Up first, notice we're going to be focusing on angle A, and we want sine of A. If it helps you, we can recall that SOHCAHTOA will help us find those ratios. Sine is opposite over hypotenuse. Looking at angle A, the side opposite angle A is little a over the hypotenuse C. That is A divided by C. Cosine is adjacent over hypotenuse. So again, focusing on angle A, the adjacent side is B over the hypotenuse C. And now we'll be focusing on B. Looking at B, sine of B, again we have opposite over hypotenuse. So that is little b over c. And then cosine of b, we have adjacent over hypotenuse, or A divided by C. Now the question says, what do you notice about the values in this table? Notice that A divided by C and A divided by C occurs in two places. We can say that sine of A is equal to the cosine of B. Similarly, we have B divided by C and B divided by C, meaning cosine of A is equal to the sine of B. So this will lead us into another theorem. Recognize that A and B are complementary, They're complementary because they add to 90 degrees. Angles A and B must sum to 90 degrees. And now that we have sine of A equaling cosine of B, that's going to lead us into what we call the complementary angle theorem. Cofunctions of complementary angles are equal. So we need a definition now for cofunctions. Cofunctions are the trigonometric functions whose values are equal when performed on complementary angles. As we saw in that example, sine and cosine were the same when performed on complementary angles, meaning we can call these cofunctions. We also have tangent and cotangent are cofunctions, and secant and cosecant will also be cofunctions. In example 8, we want to use the complementary angle theorem to find the equivalent statement. So in part A, we're given sine of 35. We want to have an equivalent statement to that. A couple things to note. We want to know what the cofunction of sine is. Sine and cosine are cofunctions. So we'll be looking at something in terms of cosine. And we also want to know the complement to 35 degrees. Remember that complementary angles have to add to 90 degrees. So let's use those two things. Sine of 35 degrees, we can use the cofunction cosine, and to find the complement to 35 degrees, we will subtract 35 from 90. And here we get cosine of 55 degrees. Cosine of 55 degrees is the same as sine of 35 degrees. They're equal. In part B, we're looking at tangent of pi thirds. The cofunction to tangent is cotangent. And we're looking for the complement to pi thirds. It's a little bit trickier this time because it's in radians, but if you recall, we have a way to find what 90 degrees is in radians. If you don't already know it, let's do that off to the side. 90 degrees divided by 1, we can multiply by pi radians divided by 180 degrees. This will give us pi halves. So 90 degrees is the same thing as pi halves radians. So we'll have the cofunction cotangent. We'll look at 90 degrees or pi halves radians and subtract the pi thirds to get that complementary angle. It looks like we need common denominators. We'll get 3 pi sixths minus 2 pi sixths, leaving us with cotangent of pi divided by 6. This is the same thing as tangent of pi thirds. And then for secant, we want again an equivalent statement. Let's use the cofunction of secant, which is cosecant. So we have cosecant. Again, we need to find the complement to pi twelfths. We'll start with 90 degrees or pi halves radians and subtract pi twelfths. We'll need to get an equivalent denominator. That will be 12. So we have 6 pi twelfths minus pi twelfths, which will give us cosecant of 5 pi 12ths. And this is the same thing as secant of pi 12ths. They have the same value. In example 9, we want to calculate the values of these expressions without using a calculator. Recognize right away that tangent and cotangent are cofunctions. That's going to be helpful. Note that these are cofunctions. Also, 75 plus 15. 75 degrees plus 15 degrees is 90 degrees, which means these are complementary angles. So since we have complementary angles and cofunctions, we can use that theorem from earlier. Let's rewrite the denominator. Let's leave the numerator as it is for now, and let's use the complementary angle theorem to help us rewrite cotangent of 15 degrees. We can write that as tangent of 90 degrees minus 15 degrees. This gives us tangent of 75 degrees divided by tangent of 75 degrees. Those numerator and denominator are the same, so we get 1. And in part B, notice again we have cofunctions. Sine and cosine are cofunctions. And notice that those angles add up to 90 degrees, so those angles are complementary angles. We can again use the complementary angle theorem. Let's keep cosine as it is for now, and we can rewrite the sine as the cofunction cosine, and then we need to do 90 degrees minus 52 degrees. Here we get cosine of 38 degrees minus cosine of 38 degrees. This gives us 0. So using the complementary angle theorem, we were able to calculate those exact values using the fact that they are cofunctions and we had complementary angles to find the exact value, and we did it all without a calculator.